So I'd like to talk about two topics, and the first topic follows directly from the comments that Peter and Steve made, looking at the intersection of the existing infrastructure and the evolution of our petroleum fuels and the petroleum-based fleet, and the evolution of new fuels like biofuels. So I'd like to talk about two topics, looking at the evolution of technologies over time. And so the first topic is, again, looking at these two interdependent technologies. So how will biofuels and engines evolve? So I'll spend the bulk of my 15 minutes talking about that. And then what I'd like to do is just touch upon a second topic, which is also looking at technology pathways, but think about it from the perspective of parallel technologies. So when we talk about fuels and engines, they are interdependent. You have to use fuels and engines, hence the first topic. The second topic is looking at how do you consider other technologies and their evolution when they aren't necessarily codependent upon each other. And so I'd like to raise a few topics there, a few issues there. I probably won't answer all your questions, or I'll probably pose as many questions as I'm able to answer here. And these two topics are based upon a couple of reports based on workshops that we at Sandia hosted over the last couple of years. And I do have copies of the more recent one with me. So anyone interested, I'm happy to unload those on you so I don't have to carry them home with me. So first, let me talk a little bit about biofuels. I'll go over this very quickly since Steve covered most of this. But clearly, we want to get beyond the current set of biofuels that are in place. So corn-based ethanol or biodiesel based on oil seeds and oil crops that could potentially compete for important resources for food. So as we think about this next generation of biofuels, we want to take advantage of other sources of biomass like cellulosic sources or algae. So as we think about cellulosic sources, cellulose is the most abundant plant material on the planet. But one of the challenges here is how do you actually break it down and get rid of the hard lignin that holds the plants together and really liberate the carbohydrates that you want to use to actually create the fuels that would be useful. So as you think about how you how you work with these types of materials, you want to be able to liberate the fuels or the cellulose materials so that you can make the fuels that are of interest. But as you think about these new fuels that we're going to be making, whether they're out of these cellulosic sources or algae or other sorts of venues, you have to think about what exactly is the fuel that you're going to be making. And there's been a big push, as Steve mentioned, to looking at making these drop-in fuels that are infrastructure compatible, that you can use with existing engines in either the ground vehicle fleet or in aviation. But even with the ability to have some fungibility and blendability, the chemistry is going to be different. It's not going to look exactly like a petroleum-based fuel. And even if you look at petroleum-based fuels, there are variations from within the supply and what those chemicals and molecules look like. So the first point I'd like to make as we talk about the evolution of biofuels and engines is that chemistry matters. Now, historically, you haven't had to know a whole lot about chemistry to make an engine. So going back to the development of the modern four-stroke spark ignition engine or the diesel engine, neither Nicholas Otto or Rudolf Diesel really understood the chemistry. That came a little bit later, about 50 plus years later, when Semenov earned the Chemistry Nobel for understanding that combustion is made up of a series of chemical reactions that produce heat and help generate the forces that could drive these engines. So historically, you haven't had to think much about the chemistry of your fuels when you are producing engines. But as we look to advanced engine technologies, we're going to see a lot more interdependence between fuel chemistry and what happens in these engines. So if you look at typical engines, spark ignition engines, these engines, the combustion chemistry and the ignition in these is controlled by the spark. So every cycle that your engine is running, there's a spark, and that causes the initiation of combustion. In a diesel engine, the combustion is initiated by the injection of fuel. So there is compression of the hot airs and the gases, and then you add the fuel, and this is what causes the the combustion to occur. So you have these physical controls that enable you to control when the combustion processes are going to start. Now, the challenge is that as we want to drive towards higher efficiencies, we want to look at novel engine concepts. And many of these concepts are taking advantage of low temperature combustion strategies. And these strategies are at lower temperature than traditional spark ignition or diesel engines, which take place at around 2,500 Kelvin. So these lower temperature combustion strategies take place at lower temperatures, typically less than 1900 K. And this is so that you could have, so that you could operate these engines with an excess of oxidizers, so either air or exhaust gases that you recirculate in the engine, and so that you could have more complete burning of the fuel. So this will enable you to have more efficiency in these sorts of designs. But designs like HCCI, homogeneous charge compression ignition, rely upon chemistry to time the ignition. So you don't have a spark. You don't time it by when you inject fuel into the chamber. You actually depend upon the chemistry of the chemical processes of the fuel and air mixing and initiating the series of combustion reactions. So what does this mean? Well, what this means is that as you try to drive towards these more efficient strategies, you're going to really be dependent upon the chemistry of what occurs in these engines. And this chemistry, again, is going to vary depending upon what fuel source you have in there. So one of the aspects of chemistry that we care about is, for example, the ignition, so the instantiation or the initiation of combustion. So as Semenov noted, and as we've done much more research over the last 50 plus years, ignition is one area of combustion where the detailed chemistry matters. So again, the combustion and the ignition is instantiated by a series of chemical reactions of reactive species called radicals that basically chain branch, and there's a nonlinear mechanism here. So the important point is not to be able to follow all the arrows in the chart, but the point is that the nonlinearities of the system, that once you begin a reaction, it generates many, many more reactions that cause basically a nonlinear feedback, so that you have this continuation of these sets of chemical reactions without extinguishing them in the combustion process. So as you think about this complex set of reactions, the chemistry is going to matter. And if you change your fuels, it's going to dramatically change what chemistry happens in these devices. So the point here is that as you look to these engine technologies, especially the novel low temperature combustion strategies, and you depend upon the chemistry, what you're going to want to do is you could try to tune your engine to the particular fuel that you're going to be using. But any small changes in that fuel is going to change what happens in the engine. And so you're going to, even if you tune it for what you think your biofuel or what your advanced fuel is going to look like, any small compositional changes will influence that chemistry. So I see in the future for engines that you're going to have to really understand and characterize your fuels well, understand the chemistry better, so that you could be able to have this coevolution of your fuel stream and the engine technologies that take advantage of them. So that's the kind of the first point that I wanted to make.